So we will try to get through this pretty quickly. This is our continuation of the historical development of the atom. What we need to begin with is what we talked about the other day of how elements behave. So we talked a little bit about metals, we talked about nonmetals, and we talked about metalloids. So to list those out so you can actually put them into your notes would probably be a good thing. So we have these three different things. We have metals. So some of the characteristics of metals that you may or may not be aware of are things like they are conductors of heat and electricity, they are shiny, and they are solids. The one exception we talked about in class was mercury. Mercury is a liquid at room temperature. They are malleable, which is a fancy word for you can pound them out into a sheet. And they are also ductile, which means that you can turn it into a wire. An example of a metal that we have used in our class the last couple of days has been that magnesium ribbon. If you recall, it was a long, skinny strip. You didn't see what it really looked like. So this is what I get out of the back room of the stock room. It is a long, skinny piece of metal, and it has been pounded into a sheet and then rolled into this roll so that we can use it. It transfers well. Here's a brand new roll. Magnesium is definitely able to be turned into a sheet. You also recognize aluminum as being malleable. We have aluminum foil, and actually aluminum foil comes in lots of different thicknesses. That's because it's malleable and we can decide how thick or thin we want it to be, and we use a different machine to roll that out. Nonmetals, as I'm sure that you're aware, are the exact opposites of metals. They are poor conductors of electricity and heat. You don't really want to use those to try to get something hot. Many of them are gases at room temperature. In fact, all of the gases would fall under the nonmetal category. The solids, if we have a solid nonmetal, it would be considered brittle and dull. So it doesn't have that shiny luster to it. I have here in front of me a sample of sulfur. The problem with sulfur is it stinks, and I forgot to get forceps. I'm just going to pick it up with my finger. This stuff is nasty. I'm going to have to wash my hands before I go home. So sulfur, as you can see, is a nice bright yellow. I don't know if you can see the color in our screen very well. It is yellow, and it is very brittle. It is like a dry powder. It stinks like butt. So if we were to try to crush it, I don't have anything to crush it with. I was not prepared for this part. So if we were to push on it, it breaks into these dry crumblies. As you can see, it broke into powder. I don't want to touch it with my hands. I would crush it with my fingers, but literally I would smell like butt for the next 3 hours. So sulfur is a stinky non-metal. It is a solid that is brittle. It is dull. It doesn't have that shiny luster to it. That is the term we use for metals. They have luster. And the last one is metalloids. For a metalloid, they are semiconductors. Again, you've probably heard of that term before. They are often, no, not often, they're all solid at room temperature. They are less brittle, but they are not as malleable nor as ductile as real metals. So they kind of take on the characteristics of both metals and nonmetals. We mentioned in class that silicon is like the poster child for a metalloid. So this is silicon. As you can see, it's kind of shiny, and it has some luster to it. However, it is also brittle. I can show you by some of the other stuff that you heard me shaking out a moment ago. It breaks into these little tiny little pieces parts. And so they are brittle in the sense that we can't really turn it into anything while it's a solid. If we were to melt it, I don't think I have the melting point here. If we were to melt it and then re-solidify it back up again, then we would start to see some of the other characteristics of how we can turn it into what we use in our computers. Silicon chips can be, they conduct sometimes, they don't conduct other times. So that is the idea of metalloids. Those samples that you've seen, they are real-life examples. I can show you more in class of some of those things as well. So as we continued working through, all of these things were known through the early 1800s. And by the mid-1800s, there were quite a few questions that still remained. But we had two facts. We knew these two things to be true. We knew that elements cannot be broken down any further. That is what an element is. It was that thing. We can't break it down. The second fact that we knew was that some elements have similar properties. So they would know, well, this thing happens to be an element, but this other element reacts a lot like it. The prime examples are lithium, sodium, and potassium. And those three metals are very light. They are less dense than water. They would float on water. And what happens is they all react very vigorously with water. I could show this. I don't want to kill myself with nobody here at the school while I'm recording this. So I'm not going to show you. I'm going to link a video right underneath this one. It won't be of me. It's of all three of these things being added to water. The actual thing of potassium isn't as, the person who does it is very good and uses a very small piece of potassium. If you use a larger one, it would be very vigorous, and you would know what I'm talking about when you see it. So again, even though we knew these things, that elements can't be broken down, they have similar properties, that lithium, sodium, and potassium, they all look the same. They're this shiny, soft metal. We can cut them and see that they're shiny. But when they react with water, they're similar, but we knew they were all three different substances. They still didn't know what was causing these elements to have these similar characteristics. So there had to be something going on inside these little pieces parts, inside what we then had determined to be called atoms. And we knew that atoms couldn't be divided. We couldn't break them down any further. And so we came up with some early models. Scientists were trying to figure out, what can we do? What's going to happen with these things? Let's try to experiment with these things. And so as they kept sitting around talking, one of the people that developed an idea was named Thompson, J.J. Thompson, and he came up with what he called his plum pudding model. He literally had been studying all day. They're trying to figure out, we've got these parts. By the way, they had done other experiments about what's called cathode rays, and they determined there's these negative particles inside of an atom. They had found electrons, but didn't really know anything about what they were doing. So J.J. Thompson was eating dinner, and he had this stuff called plum pudding. And so Thompson looked at it, and he's like, all right, so this is what I think. What do you guys think? And he proposed this to some of his friends. I don't know how well you can see that. I'm hoping it's pretty good. There was a spherical, this atom was this big spherical cloud, and the whole thing was positive with these embedded negative electrons. And those electrons, there was a specific number of them, and however many electrons there were, those all counteracted however much positive was inside that sample. Now, the crazy thing about this was they had no idea how the positive stuff was spread out. They just thought it was like Play-Doh or Jell-O or pudding that just had some positivity to it, and there had to be the right number of electrons to cancel out that positive charge. After a few years, people were like, well, this still kind of seems weird, and a man named Ernest Rutherford did an experiment. I won't even put that up there. Ernest Rutherford, they had found these things called alpha sources. Alpha particles are radioactive decay, and he took this alpha source and he designed an experiment where he was shooting the alpha source. It's hard to see that. Let me turn the lights off for us. He would shoot the alpha particles towards a film of, or a thin piece of gold foil. And the thin gold foil allowed most of the particles to pass straight through. Most of these alpha particles, which are strong, positive pieces, would pass directly through, and on this film, it would flash. There'd be a flash of light every time it hit. But every now and then, one of them would go off sideways. As you can see, like this is the straight line, and then there's some that are going sideways. And even more rare, they would bump into the gold foil, and it would flash almost back at them, like at a 180-degree angle, which Rutherford knew that's impossible. This can't be happening. What is going on, and why are these particles flying back towards us? So they realized with this experiment, Rutherford is credited with determining that the nucleus has a positive part to it. So the result of an experiment was there is a nucleus, and other experimenters, including James Chadwick and a couple other guys who was a worker in Rutherford's lab, they developed that there were positive protons and neutral neutrons inside this very dense, very small, but very dense positive particle called the nucleus. They also realized that the atom is neutral, so all of the charge of the nucleus has to be equal yet opposite charge of the electrons. So if we know that there are some number of protons, then we know how many electrons there are as well, because the atomic number is equal to the number of protons, and it's equal to, oh, sorry, that is not true. The atomic number, okay, I just said it wrong, because that is correct. The atomic number is the number of protons. This is not true. The atomic number is the number of protons. The mass number, that's what I screwed up when I was typing this. The mass number is the number of protons plus neutrons. Protons plus neutrons. And the mass number is not on the periodic table. The average atomic mass is on the periodic table. We have alluded to this a couple different times throughout the course of our class, that the numbers that are on the periodic table aren't like, you can't get that by looking at the protons. So even though they'd figured all this stuff out, they knew that there was this mass number, they knew there was atomic number, there were still a lot of questions that lingered. And one of the things that they were questioning was, why do these metal salts, like if we were to take this dry powder of this salt that we know has sodium in it, why does it burn this crazy color? Why do these things with lithium in it burn a different color? And they started to realize that they could see these colors when they analyzed the stars. So they were realizing, okay, these elements aren't just on Earth. These elements are out there in the universe as well. They make up our stars, they make up the sun, and so we started to see these different colors. Now again, how these electrons are giving off different colors is beyond anything we really need to go into a lot of depth on. It would be more of an AP chemistry, or if this were college first year chemistry, you would need to know a little bit more about it. But it brings along this new model. And so what we're going to do, these colors and the energies, we're actually going to do an experiment with this on Thursday in class, where you're going to light some things on fire and see what colors they give off. Now the colors are due to a different amount of energy of how those electrons absorb energy and release energy. So with different energies, we get different colors. And this is the one that's kind of backwards from what everybody would think. Purples and blues have more energy than reds and oranges. The red and orange is a lower amount of energy. So again, throughout all this process, what's going on, we came up with a new model that is now the current model, called the quantum mechanical model of the atom. And it is essentially saying that we have this cloud of electrons, and that cloud is a probability map of where we would find the electrons at any given time. Now, the hard part about this is where those electrons are found is really complex. And because we're talking about microscopic particles, the way that we go about this is a little bit more, to use a fancy word that you don't know yet, it's esoteric. It's something that only people that care about studying chemistry will understand. And so as a result, we will talk about it very briefly in class. It's where we're going with the next set of lecture. So the next lecture, I'm going to talk a little bit about what we call these electron configurations. It is the arrangement of where those electrons can be found. So as you work through this today, the only thing you really need to be aware of is that two people were really important. J.J. Thompson and his plum pudding model, which we now accept as being wrong. It was a good model to begin with. And then Ernest Rutherford and his gold foil experiment. He was able to determine what we call the nucleus surrounded by electrons. There were other models in between, but again, those are things that we use as tools to realize that this quantum electron model, quantum mechanical model, is much better for an atom. So next time we'll go into a little bit more depth, and we'll talk a lot about this thing called electron configurations, and then we will teach you how to use the periodic table in a way to know where the electrons can be found. We'll see you next time.